Welcome back to the You Can Do TV channel.
Daiwadag post-tensioning systems are engineered for high-performance bridge structures, delivering high pre-stressing forces and accommodating long tendon lengths. During installation, Jackson pumps operate near maximum capacity, requiring continuous service and inspection to maintain precision and reliability. Grouting operations are critical for durability, ensuring that post-tensioned elements achieve long-term structural integrity. Daiwadag's expertise extends to stay cable systems for cable-stayed bridges, where DynoBond and DynoGrip cables provide replaceable, efficient tensioning for lightweight superstructures. On major projects such as the 2.6-kilometer Sky Bridge crossing, Daiwadag supplied form travelers, post-tensioning systems, and supervised installation, supporting advanced methods like free cantilever construction. Every aspect is designed to combine technical efficiency, safety, and economic installation, meeting stringent quality standards. Construction of the St. Croix Crossing Bridge involved extensive underwater foundation work, connecting St. Joseph, Wisconsin, and Oak Park Heights, Minnesota. The bridge piers rest on caissons extending up to 140 feet below the water, with 4 caissons per pier and 10 pier columns in total. Crews floated in a prefabricated steel framing system topped with concrete, which served as a work platform with circular openings for placing the steel casings. These casings penetrated up to 25 feet of water, 87 feet of muck, sand, gravel, and soft sandstone before reaching bedrock. Excavation inside the casings removed 500 dump truckloads of material, and massive drill bits, up to 7.5 feet in diameter, were used to drill 25 additional feet into bedrock. Reinforcement cages were installed and concrete pumped to form solid foundations. Cofferdams were placed around the prefabricated deck, and a 3 to 4 foot thick concrete seal was poured underwater. Once dried, reinforced footings and pier columns were constructed, supporting 400,000 tons of bridge weight and ensuring structural durability for over 100 years. The world's first kiloton bridge girder erection machine has been commissioned in Fujian Province, southeast China. Designed for the Meizu Bay Cross-Sea Bridge on the Fujiu-Xiamen high-speed railway, the machine measures 40 meters in length and weighs over 1,000 tons. Engineered for precision and efficiency, it lifts and positions massive bridge girders, accelerating construction timelines and ensuring structural safety. The high-speed railway is scheduled to commence operations in 2022, marking a significant milestone in advanced bridge construction. Spanning the busy Saigon River in Ho Chi Minh City is a landmark cable stay structure and a crucial component of the city's ring road, linking the Mekong Delta to central and northern Vietnam. Built between 2007 and 2009, it was the first major privately funded bridge project in the country. Designed and constructed by the BBPH Consortium, comprising Germany's Bilfinger Berger and Australia's Balderstone Hornibrook, the project leveraged extensive international experience, completing months ahead of schedule and within budget. The bridge's roadway is suspended from high-strength cables attached directly to towers, which bear the entire load. BBPH's prior experience with cable-stay bridges, including Sydney's Anzac Bridge and the Centennial Bridge in Panama, allowed optimization of processes and faster learning curves. After completing deck work and cable installation on District 7, massive travelers had to be transported and repositioned to District 2, a delicate operation requiring precision, heavy lifting equipment, and careful logistics. Each transfer took roughly a week, and any equipment damage would have significantly delayed the project.
Find it, Rod?
Nope. Oh, got it. Oh my God. You're here. Thank you.
When in doubt, look in your own canoe.
Uh-huh.
Thank you. I tried so hard to get here. And we were beaten by Rob. At least we were
Paddle away.
By May 19, 2009, deck closure was completed, marking the bridge's readiness for traffic. Stretching 2.1 kilometers, the Hugh Mai Bridge now connects District 7 and District 2, dramatically improving traffic flow while standing as a modern engineering landmark. Its construction highlights advanced post-tensioning techniques, meticulous coordination of heavy equipment, and optimized cable stay installation, demonstrating Vietnam's growing expertise in large-scale infrastructure. Beyond transportation, the bridge symbolizes Vietnam's progress and commitment to world-class engineering standards. The Beechwood Boulevard Bridge in Greenfield was a complex infrastructure project requiring precise engineering and careful sequencing to ensure safety and efficiency. The bridge spans a local waterway and accommodates both vehicular traffic and pedestrian pathways, making it an essential component of the area's transportation network. Construction began with detailed site preparation, including excavation for abutments and piers, and installation of cofferdams to manage water flow during foundation work. Foundations were established using reinforced concrete caissons driven into stable soil layers, providing a secure base for the bridge. Steel rebar cages were carefully positioned inside the caissons before concrete was poured, ensuring maximum structural integrity. Once cured, these foundations supported the erection of precast concrete segments and steel girders. During the superstructure construction phase, the steel beams and floor girders are pre-assembled on the ground, then lifted and placed into position in the weekend highway closure scenario. The erection of the arches and girders is done precisely using lifting equipment, creating a solid and continuous structure. The bridge's superstructure utilized a combination of steel girders and pre-stressed concrete beams. Heavy lifting equipment positioned each girder with millimeter accuracy, while temporary supports maintained alignment during installation. Post-tensioning cables were then threaded through ducts within the beams and tensioned to provide additional strength and minimize deflection under load. Deck construction involved placing formwork and pouring high-strength concrete, followed by finishing and curing. Expansion joints, drainage systems, and safety barriers were installed to meet design standards and ensure durability. Throughout construction, strict quality control measures were applied, including material testing, alignment verification, and load testing. By integrating modern construction techniques with careful project management, the Beechwood Boulevard Bridge was completed efficiently, providing a safe and durable crossing that enhances connectivity in Greenfield, while demonstrating the precision and technical expertise required for modern bridge construction. Duff's Bridge and Marley Bridge over Dingo Creek were handed over to the Greater Atari City Council in 1989. Both were single-lane Allen timber truss bridges, increasingly expensive and difficult to maintain due to the high-quality timber and skilled labor required. Marley and Duff's Bridges, completed in 1900 and 1926 respectively, were the council's last remaining timber truss structures. Restrictions imposed on heavy vehicles, reducing load limits from 25 tons to as low as 2 to 12 tons by 2008, highlighted the urgent need for replacement. These restrictions impacted local businesses, farms, rural communities, and tourists. With 2 years of future bridge funding and a $2.5 million grant, the council proposed replacing the bridges to provide safe, reliable, and cost-effective infrastructure. project began with extensive site investigations and options analysis, focusing on 3 key criteria: cost, functionality, and traffic impact. 3-span, 2-lane bridges were selected for both sites. Marley Bridge was retained on its existing alignment to save approximately $1.4 million in approach roadworks, while Duff's was initially proposed on a new alignment downstream to facilitate construction access for heavy plant, precast items, cranes, and concrete trucks. During design, an indigenous artifact was discovered along Duff's downstream alignment, prompting the project team to shift the new alignment onto the existing route. This minimized environmental impact and avoided delays, while enabling the bridges to be designed nearly identically, optimizing construction efficiency. Foundations for both bridges relied on permanently cased large-diameter board piles penetrating 3 meters into bedrock, recommended by regional GE Technical Solutions. This method also mitigated scouring risks from Dingo Creek's fast-flowing waters. 2 piles per pier were installed on either side of the existing timber decks, eliminating the need to drill through the old structures and improving safety by reducing time spent near traffic. Steel-encased concrete piles were extended to the headstock level. The use of precast members minimized in-water work, reducing exposure to flooding and high-risk height operations. Site preparation included installing crane pads, temporary support structures, and storage for precast components. Demolition of the old timber trusses was complex due to unpredictable truss behavior, as elements transitioned from tension to compression during lifts. Each span required detailed analysis, engineering sign-off, and careful propping, strapping, and chaining. Duff's Bridge, over 16 meters high, required a licensed company and a 500-ton all-terrain crane for span removal. Spans were lifted, lowered, and disassembled at ground level to improve safety, while temporary steel supports were erected to stabilize the trusses during demolition. Where the crane lacked sufficient capacity, spans were cut and removed in 2 sections. At Marley, demolition improvements included reduced crane standby times and innovative temporary support structures. Steel headstocks were integrated into the permanent pier design to support temporary steelworks, allowing reuse of the same structures for both bridges. This minimized risk, cost, and construction time. The process incorporated lessons learned from Duff's, including time-lapse analysis to identify critical path activities. Marley's timber truss was dismantled with a restricted license using a 60-ton crane, with careful removal at ground level, reducing height work and enabling reclamation of sound timber for sustainable reuse. Construction of the new decks relied on precast, pre-stressed concrete planks with transverse post-tensioning bars, eliminating the need for in-situ decks and allowing immediate traffic access after installation. Edge planks were lifted using scaffolding for safe access at height. Pre-routed transverse bars encased in PVC sheaths provided long-term corrosion protection, while grouting under a 100 kilonewtons load ensured plank consolidation. Bars could be replaced in the future if maintenance was required. Conduits were installed in transverse bar holes to maintain alignment. and small hydraulic jacks against fabricated steel blocks ensured precise placement. At Marley, a second 200-ton crane lifted distance spans working near maximum capacity due to the congested site. Trial assembly of precast planks in Brisbane allowed fault correction and ensured quality control before on-site installation. Scaffold crews immediately installed infills for safe working conditions, while precast abutments, headstocks, and curtain walls reduced closure time. Precast production efficiency was maximized by casting identical planks, minimizing variations in length, skew, or penetration, reducing cost and delays. The heavy lifts at Marley were completed with the 500-ton crane used at maximum efficiency. Barrier rail sections were pre-assembled and installed before scaffolding removal, and all infield formwork was cast with corrosion protection caps for future maintenance access. Duff's Bridge reopened after 7 days of closure, while Marley used the full 10-day window to install headstocks, decks, and guardrails. The strategic use of temporary steel support structures allowed them to serve as emergency crossings, providing sustainable infrastructure reuse and community resilience. Flooding events in early 2013 did not affect completion dates or costs due to careful planning and minimization of in-water work. Deck widths were increased to 2 lanes, and design loadings accommodated 44-ton trucks and 68-ton B-doubles, enhancing safety and supporting local economic growth. Flexible joints, guardrails, and signage completed Marley Bridge, achieving high-quality, innovative solutions normally seen in larger infrastructure projects. Continuous improvement throughout the project ensured long-lasting, cost-effective community infrastructure. The UAE's first overseas railway bridge is under construction, linking Khalifa Port to the national railway network. Part of Package B of the Etihad Rail project, connecting Tarif and Said Shuaib, this 1-kilometer-long bridge will enhance freight transport efficiency, speed, and reduce trade costs in the region. Currently, 50% of the bridge's construction is complete. The project will use approximately 18 300 cubic meters of reinforced concrete and 4 117 tons of steel, making it a major engineering milestone for UAE's infrastructure and regional logistics development. The Shah Ruwais railway line, a key segment of the UAE's Etihad Rail network, involves highly coordinated engineering and construction processes to ensure a durable, safe, and efficient rail corridor. Construction begins at the welding plant, where prime rails are carefully loaded, handled, and prepared for joining. Flash butt welding is employed to form long, continuous rails, ensuring high-quality, consistent rail connections critical for high-speed and heavy freight operations. Once welded, the rails undergo grinding to achieve smooth joints, maintaining track alignment and passenger comfort. On-site rail unloading and sleeper placement follow. Sleepers are positioned precisely, maintaining proper gauge and spacing before rails are laid on top. Fastenings are initially fixed to secure the rails, allowing further operations such as aluminothermic welding for final joining. After welding, fastenings are released temporarily to allow stress relief and rail alignment adjustments. Subsequent ballast layers are distributed along the track bed, with the first layer providing foundational support and drainage, followed by tamping to compact and stabilize the track. A second ballast layer is then applied, leveled, and tamped to ensure uniform load distribution. Track leveling, alignment, and dynamic stabilization are performed, guaranteeing smooth operation under heavy freight loads. Ballast profiling and track brushing remove excess material, while vacuum cleaning ensures sand and debris do not interfere with rail performance. Topographic surveys are carried out throughout the construction process to monitor track geometry and ensure alignment with design specifications. Rails are cut and installed where required, with rail pullers used to adjust rail tension. The track is then de-stressed to release residual stresses from welding, minimizing the risk of track deformation over time. All welding operations, including aluminothermic welding, are subjected to rigorous quality control, ensuring weld integrity, dimensional accuracy, and alignment. Construction railway operations are carefully managed, with a dedicated traffic office coordinating train movements and shunting operations at turnouts. Safety remains a top priority, with a zero-accident philosophy embedded across all work phases. Personnel undergo safety induction and adhere to strict operational protocols during all stages, from welding and ballast handling to track leveling and final inspections. Once the primary track installation is complete, final quality checks ensure all rails, fastenings, and sleepers meet strict tolerance requirements. Track dynamic stabilization is performed to simulate train operations, ensuring the track responds correctly to load and vibration. Additional ballast adjustments, sanding, and vacuum cleaning are undertaken to remove debris and maintain track integrity. The final stage includes comprehensive safety and operational testing. Fastenings are checked and retightened where necessary, and final controls confirm alignment, gauge, and weld quality. The construction of the Shah Ruwais line is a prime example of modern railway engineering, combining mechanized processes, precision surveying, and rigorous quality control. Each stage, from flash butt welding at the plant to ballast profiling on site, contributes to a reliable, high-capacity railway capable of supporting both freight and passenger services in the UAE. Throughout the project, advanced construction methodologies, including automated welding, mechanized track laying, and dynamic stabilization, ensure efficiency and minimize risks. The use of high-quality materials, careful planning, and adherence to international safety standards has enabled the Etihad Rail project team to deliver a robust infrastructure asset, connecting industrial hubs, ports, and logistics centers, and supporting the UAE's economic growth and regional trade objectives. By integrating safety, precision, and technological innovation at every stage, the Shah Ruwais railway line demonstrates the UAE's commitment to world-class infrastructure development, providing a modern, reliable rail link that will serve the country for decades to come.
The Pacific Coast Highway, State Route 1, an iconic stretch of roadway along California's coastline, faces a perennial challenge: unstable slopes that pose hazards to motorists. To address these risks, Caltrans has initiated a comprehensive rock mitigation project aimed at protecting both the highway and its travelers. Scheduled intermittent closures on Monday, November 25th and Tuesday, November 26th will occur between 6:30 a.m. and 4:30 p.m., spanning from south of Las Posas Road to north of Deer Creek Road. Drivers should anticipate delays of 20 to 30 minutes and are strongly advised to consider alternate routes. Safety and traffic control form the backbone of this operation. The California Highway Patrol will maintain an on-site presence, coordinating with flaggers to direct traffic safely through the area. Advanced changeable message signs have been strategically placed to provide motorists with real-time updates on lane closures, expected delays, and recommended detours. The rock mitigation process is executed in carefully planned phases. The first phase involves highly skilled rock climbers scaling the steep slopes adjacent to the highway. Equipped with specialized harnesses, ropes, and hand tools, these climbers systematically identify and dislodge rocks that could become hazardous if they fell onto the roadway. This methodical removal process not only mitigates immediate risk, but also prepares the slope for subsequent stabilization measures. Each rock is carefully lowered or secured to prevent uncontrolled rolling, ensuring that both personnel and traffic remain safe throughout operations. Following the climbers' work, a second phase of mitigation will implement more permanent measures. Helicopters will be employed to install engineered rock retention nets across the hillside. These nets are designed to conform to the natural contour of the slopes, anchoring into bedrock, and absorbing the energy of any rocks that may loosen in the future. This technique, known as Rockfall barrier installation, is widely recognized for its effectiveness in preventing debris from reaching active roadways while maintaining the ecological integrity of the hillside. Throughout the project, careful coordination between ground crews, climbers, and aerial teams ensures that each step is executed with precision. The combination of manual rock removal and advanced netting technology represents a comprehensive approach to slope stabilization, minimizing risk to drivers while addressing long-term geological hazards. Beyond the technical execution, this initiative highlights the broader commitment to public safety and infrastructure resilience. By proactively managing natural risks along State Route 1, Caltrans demonstrates how engineering solutions can harmonize with California's challenging coastal terrain. Once complete, these measures will provide motorists with enhanced protection against rockfall incidents, while preserving the scenic character of one of the nation's most celebrated highways. Rock mitigation along State Route 1 exemplifies the integration of skilled labor, modern engineering techniques, and strategic planning. From climbers navigating sheer rock faces to helicopters deploying robust netting systems, every aspect of the project underscores meticulous attention to detail. Motorists are encouraged to remain informed about closures, follow guidance from flaggers, and exercise caution when traveling near active work zones. Ultimately, this project ensures that both safety and operational efficiency are maintained, securing State Route 1 for the countless drivers who traverse this iconic coastal corridor every day. The Crema Marfil Codo Quarry in Pinoso, Alicante, stands as the world's largest source of premium cream-toned marble, a landmark within the global natural stone industry. Operated by Levantina, this vast open-pit quarry is internationally recognized for producing crema marfil, a material valued for its warm coloration, refined veining, and structural consistency. Beneath its iconic surface lies a sophisticated extraction operation, shaped by decades of engineering evolution. At the heart of the quarry's workflow is a multi-bench terrace system that enables controlled access to deep limestone layers. Each bench exposes a new horizontal slice of the Codo formation, ensuring efficient segmentation of marble deposits while maintaining high safety standards. The extraction process begins with detailed geological mapping and structural analysis. Engineers use core drilling, fracture scanning, and digital terrain modeling to identify optimal cut zones where block integrity is highest. Diamond wire saws, equipped with industrial-grade beads, glide across the limestone with precision, separating massive volumes of stone from the quarry face. Vertical and horizontal wire cuts define each block's dimensions, minimizing internal stress and reducing microfractures. Once freed, hydraulic excavators and pneumatic jacks gently tip the blocks onto cushioned beds of dust and crushed stone, preventing impact damage. Heavy-duty wheel loaders transport the rough blocks to designated staging areas, where they undergo the first visual and structural quality inspection. Advanced classification methods ensure that only high-grade material proceeds to processing facilities. Inspectors evaluate chromatic uniformity, grain density, and veining distribution, attributes that give crema marfil its signature elegance. Blocks meeting export specifications are then shaped into standardized volumes for efficient transport. Automated scanning systems record dimensional data, creating a complete digital trace for each block as part of Levantina's quality management. Environmental stewardship is embedded in quarry operations. Water used during cutting and dust suppression is continuously recycled through settling ponds and filtration systems. Bench sequencing is planned to minimize landscape disruption, while continuous monitoring ensures slope stability and controlled bench progression. Overburdened material is repurposed for internal haul roads or stored for future reclamation phases. The scale of the quarry allows Levantina to maintain consistent supply for global architectural markets. From luxury flooring systems to facade cladding and interior surfaces, crema marfil's technical performance, high compressive strength, low porosity, and excellent polish retention makes it a favored material in high-end construction and design. As production continues across multiple extraction fronts, the Crema Marfil Codo Quarry remains a benchmark for large-scale natural stone engineering. Its combination of geological richness, cutting-edge extraction technology, and rigorous quality control reinforces its status as the world's leading source of premium cream marble.
Workers coordinate with engineered joists to construct floors efficiently in Princeton, Ontario. These joists almost look too light to hold an entire floor, but they lock into place like seasoned veterans of steel. The delivery and handling are carefully orchestrated, with crews moving each pre-cut piece into position to avoid any damage. Pre-punched service holes streamline the workflow, letting electricians and plumbers fit their systems without delay. It's surprising how such a seemingly simple feature can shave hours off installation time. Once the layout is confirmed, assembly begins with joists aligned across the steel frame. Each connection is checked for level and stability, ensuring that the floor will support both weight and stress safely. The sequence of assembly feels almost like a synchronized puzzle, where every piece has its exact role. Fire-rated design adds another layer of assurance, giving the UL and ULC 1-hour rating. Installing for wood walls involves 5 distinct steps: handling, layout, assembly, installation, and floor sheathing. Floor sheathing secures the structure, bridging joists to create a stable, ready-to-use platform. Seeing the joists fit together so seamlessly is oddly satisfying. You wouldn't guess it's all steel until you step on it. Tradespeople move confidently across the site, their workflow enhanced by the efficiency of Total Joist's engineered design. The system supports various building types, from multi-residential projects to hotels, providing a complete steel floor solution. Engineers from Princeton stay involved throughout, guiding installation and answering questions to maintain quality. This setup looks deceptively simple, but every move reflects careful planning and real-world durability. Since long-standing construction experience blends naturally with modern German engineering at Wehrhahn, vertical AAC wall elements gain a reliability that fits today's residential building pace. These AAC panels are produced with transport reinforcement, giving each piece the durability needed for upright handling on site. The method looks straightforward, yet the way the panel responds during lifting makes the process feel grounded and secure for everyday housing projects. Installers appreciate how the material stays light but firm, especially when the crane keeps the element in perfect vertical posture. The panels, uniform density guarantees even curing across the entire height of the wall. Operators prepare the working zone by positioning incoming AAC elements near the setting line, creating a smooth flow between each lift. This part isn't the first task in name, but it sets the entire rhythm by letting the team guide every panel in a predictable direction without confusion. Embedded markings on the panels help crews align vertical joints without measuring each time. Mortar lines are positioned to form the landing track for the next panel, keeping the surface ready for contact. The reinforcement embedded during manufacturing provides load support during handling, making the crew feel like weight distribution is cooperating instead of resisting. A quick visual check ensures there are no loose edges before the lifting gear moves in. When the crane operator attaches the lifting device, the AAC panel is steadied to stay entirely upright, keeping its geometry intact. Slight angle adjustments help set the panel into its future slot, and installers monitor both edges so no corner drags or shifts. As the panel drops into its mortar bed, the element responds instantly, settling with a confident stop that signals proper seating. That moment the panel locks in place always gives a small jolt of satisfaction, like everything just clicked. Crews make tiny taps to line the vertical joints so the wall follows a continuous plane. Clamp tools assist when two adjacent panels need encouragement to stand flush. The next lift follows without delay, showing how vertical AAC installation avoids the slower, repetitive stacking of conventional brickwork. As the wall grows in height, the pattern looks consistent, thanks to the manufacturing accuracy from Delmenhorst and its long history of refining AAC technology. Once mechanical ties connect the top portions, the wall section gains its full rigidity and moves toward finishing without demanding additional waiting time. This precise fit minimizes the need for post-installation adjustments. The result is a structural segment that fits residential layouts cleanly and keeps installation crews progressing at a steady pace. You wouldn't expect precast wall erection to unfold with such control, especially when each lift depends on the crane reacting instantly to the crew's signals. Every lift demonstrates the importance of precise hook alignment for structural accuracy. The crew manages each lift while the crane handles the weight, creating a steady partnership that keeps the job moving with confidence. Proper taglines prevent rotation errors and maintain panel stability during placement. Seeing that first panel leave the ground gives a quick jolt of anticipation. Every move here depends on coordination that ensures safe handling of heavy panels. The setup phase takes over the site as workers mark out the footing lines and prepare braces for the incoming panels. Survey points confirm alignment targets so each wall section can match the structure's layout later. Accurate brace placement distributes load evenly while panels are set. The crane operator waits for the signal, keeping the hook centered to avoid unwanted drift. Ground workers guide the motion using taglines, making sure the panel rotates correctly before it approaches its final position. Funny how one windy moment can make everyone steady their footing, almost like the job suddenly tests your balance. As the panel swings into place, the alignment team calls out fine adjustments until the lower edge meets the foundation line. Setting the panel onto its base plate marks one of the most focused moments. Workers inspect the bearing pads, ensuring they sit evenly under the panel weight. Temporary braces attach quickly, creating enough stability for the crew to release the crane hook. Verifying pad seating prevents uneven load transfer to the foundation. You almost feel a tiny pause from everyone right after the hook releases. The team then moves to torque the brace connections, checking each bolt for proper seating. With several panels installed, the structure begins forming consistent segments. One thing that hits you is how fast the site transforms once 3 or 4 panels stand together. The crane keeps cycling through picks, while the ground team keeps the rhythm steady, without relying on speed alone. A random thought pops up when seeing the panels line up so perfectly. It's like the building is eager to reveal itself piece by piece. Each wall is inspected again, confirming plumb alignment and base contact. As the final panel seats into position, the reinforcement team moves in to secure connections between adjacent sections. The subtle clunk when panels meet always gives a small spark of excitement. Final bracing completes the temporary support layout, leaving the structure ready for the next construction stage once grout and tie connections follow. Final checks of connections and braces ensure the wall's load-bearing capacity meets design standards. How does the team ensure each roof slab fits perfectly atop supporting walls? Careful alignment ensures load distribution matches structural plans. Workers attach temporary braces while the crane holds each slab steadily. Taglines guide rotation to fit each slab precisely onto supporting walls. Checking bearing pads prevents uneven settling under the slab weight. Once seated, bolts and braces are torqued to specification, locking the slab safely. The process highlights teamwork between human operators and lifting equipment. Panels connect smoothly, forming the structural roof deck. Every placement counts for long-term structural stability. Every light floor panel contributes to a lightweight but robust floor deck. Ensuring each panel aligns perfectly with the supporting beams is crucial for structural stability. Workers position the panels carefully while checking for gaps and alignment, ensuring the base frame is fully ready. Overlooking even a single misalignment could compromise floor performance under stress. Each adjustment counts to prevent stress on the steel structure. Once aligned, panels are secured with bolts to the frame. Workers inspect connections to confirm tight seating, reducing risk of movement under load. Temporary supports hold the panels steady until all fastenings are verified. Mechanical lifts assist in placing additional panels, maintaining workflow without overexerting crews. Verification of bolt torque ensures long-term joint reliability. Attention to detail prevents interference with future installations. The team moves methodically along the span, positioning, securing, and checking each slab. Checking edge gaps between slabs ensures smooth load transfer. Safety protocols keep operations smooth, while efficiency tools reduce manual strain. The combination of human oversight and mechanized handling accelerates the installation process. Panels are cross-checked for levelness to maintain a flat surface for finishing works. At the final stage, alignment is double-checked, and the floor deck becomes a coherent, lightweight platform ready for finishing works. Every slab contributes to the overall integrity and load-bearing capacity of the structure. The installation sequence highlights how pre-engineered components maximize efficiency and reduce construction errors. The workflow exemplifies how lightweight steel floor systems can be installed effectively with proper coordination. Insule wall panels, previously exclusive to commercial buildings, now fit seamlessly into family homes. Each panel slides into place along a preset line, simplifying wall installation while maintaining alignment and consistency. Pre-cut service ducts are included, making it easy for electrical and plumbing connections to be integrated without extra adjustments. Installers can line up the walls quickly, following the panel design that guides positioning naturally. The first lift sets the pace for subsequent panels, letting crews maintain a smooth, predictable workflow. Mortar joints are prepared to receive the next panel, and the walls hold firm as each unit is lowered into position. Seeing these panels click into place feels oddly satisfying, like every piece knows exactly where it belongs. Internal joints are plastered using traditional methods, giving a reliable base for further finishing. Achieving a flat painted surface is straightforward when the Dulux Acrotex coating is applied seamlessly, covering walls in a consistent layer. The coating's quick drying time helps reduce downtime between steps, keeping the pace consistent. The quick coverage makes finishing much faster than expected, and the texture holds perfectly. Panels maintain their vertical orientation easily, allowing adjacent elements to align without conflict. Clamps and minor adjustments ensure flush joints and consistent wall planes, reducing the likelihood of gaps or misalignment. That small tap to adjust a joint almost looks ceremonial, a final handshake between panels. The roofing system combines insulation, ceiling, and panels into one integrated installation. Panels are lifted into place and fixed with roof screws that extend across long spans. Fascia flashings are secured in tandem, preparing the gutter while keeping assembly on schedule. It's surprising how smoothly the roofing elements lock together without needing extra tweaks. Insulation is integrated from the start, maintaining energy efficiency without additional effort. Long span panels span across sections seamlessly, and the work continues without slowing down for separate adjustments. The sequence allows multiple elements, roof, insulation, ceiling, to be installed as a single workflow, saving labor and minimizing errors. The combination of pre-cut roof panels and insulation reduces the risk of misalignment across long spans. This approach permits speedy installation for entire house sections, as the combination of insul wall panels and solar span roofing integrates all energy-efficient materials in advance. Flexible design options allow for varied residential layouts, while the installation pace ensures that construction moves quickly without compromising structural integrity. That combination of speed and precision is almost mesmerizing, but it's just the system working as intended. Each panel and roof segment fits exactly where designed, making the final structure ready for finishing and paint with minimal extra effort. The system's predictable alignment reduces rework, and crews can move on to interior and mechanical installations immediately. The way the panels hold their shape under handling is impressive for residential-sized units, almost like they have their own balance built in. Overall, the integration of walls, roof, insulation, and ceiling demonstrates a streamlined, energy-efficient method for modern housing. Insul wall panels provide reliable structural performance while reducing labor and time requirements. From pre-cut service ducts to quick roof fixes and seamless paint finishes, every element is designed for a rapid quality build. Seeing this workflow in action almost makes traditional brick-and-mortar methods feel slow by comparison. The result is a residential structure that is both visually clean and thermally efficient, keeping projects moving steadily while meeting modern energy standards.